Welcome to this video looking at the impulse force time graphs, part of the Dynamics Universe unit for higher physics. So what we're looking at today is how to calculate the impulse or change in momentum from a force time graph, and looking at drawing force time graph for different hardness of surfaces or hardness of objects, and also looking at some examples of how we can change collision situations to reduce the force. So a reminder about impulse being equal to the change in momentum, and impulse also being equal to the force times the time. And so there are two units for impulse: newtons seconds or kilogram meters per second. And impulse is a vector quantity, and change in momentum and impulse are also the same thing. And if we have a force time graph, then the impulse or the change in momentum is equal to the area underneath that force time graph. The graphs that we look at higher physics are either triangular in shape, in which case the area is half times the base times the height, or made up of rectangles and triangles, in which case you sum the total area of those two. In reality, we tend to have graphs of force over time which look more curved in nature. But as I said before, the ones that we're particularly going to look at is we're going to look at ones that are more triangular, and the peak force at the maximum value, and our impulse is half times that peak force multiplied by the time. The time is often in milliseconds. It doesn't need to be, but often the collision times are in milliseconds because the contact times are quite small. Okay, let's look at an example here. So we've got a golf ball being hit off the tee, and the force varies with time as shown there. And we need to calculate the speed of the golf ball off the tee. So the first thing we need to do is use the force time graph to calculate the impulse or the change in momentum. So it's a triangular shape, so half times the base, which is 30, about 30 milliseconds, multiplied by the 40, and that gives us 0.6 Newton seconds. And then the impulse is equal to the change in momentum, mv minus mu, so substituting in the mass, changing it to kilograms, so we've got 50 grams being 0.05 kilograms, to give us a velocity of 12 meters per second. Okay, so do just watch out in case the time's in milliseconds, the mass in grams. The force could also be in millinewtons, but more commonly newtons from there. So just take all that into account in your calculation. So we might be thinking so far, where's this useful for us to know? Well, if we're in a car, then an airbag is helping us by protecting us, and what it's actually doing is it's increasing the contact time, because the change in momentum is equal to the force times the time. If we can increase the contact time, we can reduce the force significantly. So by adding an airbag into the car, then the car and the passenger, when they have an accident, hits the airbag, the contact time is longer, and so the force is less. So there's much less damage that would occur to you. Same thing takes place if you go to the park and the playground. Then what you will notice is that underneath the slides and the swings, there could either be sand or there could be a rubbery type material, or bark chippings, and all of those work on the same basis, in that you're trying to increase the contact time, and the longer the contact time, because the surface is more squashy, so there's a longer time for you to come to a standstill, then there'll be less force that takes place. Same thing for boxing. If somebody was to punch you with their bare fist versus punching you with a boxing glove on, the boxing glove, because it has a squashy surface a little bit, then it will have a longer contact time, so overall the force will be less. and so there'll be less damage taking place. Your body, of course, takes this into account as well. If you jump off any object and you're trying to land to the ground, you will notice that you bend your legs, and so by bending your legs you're increasing the time that you're stopping in, and so therefore the force will be less. So if you jumped and you don't bend your legs, then you will probably have a too high a force and break your legs. Okay, so let's have a look at the airbag without. So the change in momentum has to be the same, because if the car's going the same speed when it comes to a complete stop, then the change in momentum will be the same, but the force time graphs can be different. Now these ones are both triangular in nature, but in reality we're looking at probably a more curved situation. So what is true is that the area underneath the graph will be the same. So if we've got a large force and a short time, as we do with no airbag, then with the airbag, if we get a lot longer time, you can see how the maximum force is much less. And what would be true in both cases is that the area would be the same if the change in momentum is the same. And given that a car would be going 0 at the end of a crash, its initial velocity, if that's the same, then the momentum and the change in momentum will be the same. Okay, so cars, as well as having airbags, also have crumple zones. They are designed to squash up when they hit objects there, and the purpose of this is the same as the airbag here, to reduce the forces to the passenger within the car. And so to do that, what we want is we have the same change in momentum per second, because that depends upon how fast we're going, but we want to increase the time that's taking place over. So we've got less change in momentum per second, and that allows us to have less force that's taking place. Okay, so we may not think that momentum and impulse are directly impacting us most days, but if we are jumping around, if we are in a car, then the safety features of the car have been designed to decrease the change in momentum per second by squashing up, and therefore because the change in momentum per second is the force, and we're trying to decrease that force. Okay, let's look at one more example here. So we've got a trampolinist on a trampoline, and we're given some information about the trampoline. So at the maximum height, their feet are 2 meters above the trampoline, and we need to calculate the speed as she lands on the trampoline. We're then given information about the speed that they move upwards, which is a little bit less than the speed that they move downwards, and that's because it's taking energy to stretch the trampoline from there. But as we will know, if we're landing on a trampoline, there is minimal force compared to the ground. If you fell from 2 meters, you would feel the force, and that's because we've got a long contact time, so a long time for that change in momentum, and that time is given at 0.5 second, half a second. And so that means that the forces aren't that great, so we're not getting any injuries taking place. So let's have a look at how we would work out our information there. So remember, we need to pull together information that we've got from our other topics as well. So we've got a height there, and we could think of that as a displacement. And so to solve this particular problem, then we're going to use an equation of motion, because we have our initial velocity, which is 0 at the maximum height, and we have an acceleration of 9.8 meters per second squared downwards, and we have our displacement of 2 meters. In this case, we've made positive being downwards, but you could make positive being upwards, in which case you would get minus 6.3 meters per second here. Okay, let's have a look at the other parts 2 and 3, looking at the change in momentum and the force. So the change in momentum, mv minus mu, is equal to the mass times v minus u. So the mass is 40 kilograms, and the rebounding speed is 5.7, but this is in the opposite direction to the 6.3 downwards. So in this case, I've made that be negative. That's why it's in red here, because it's important that it has the opposite sign. So this makes the change in momentum also negative, and that is because we've got a change in direction here. Okay, the change in momentum is equal to the impulse, F times t, and therefore the force will be the 480 divided by the time of contact, half a second, to give 960 newtons. The negative sign here is just because the force exerted by the trampoline on the gymnast is upwards. So the force of the gymnast on the trampoline is downwards. So in this case, in our question, we'd made that positive, and so the negative force means that the force is in an upwards direction, which is where they're moving next, because they're going to move back up to the height that they've got there. Okay, so what we've looked at here is we looked at how to calculate the impulse or the change in momentum from a force time graph by looking at the area underneath that graph. And we've described how force time graphs might be different for different hardnesses of surface. So if we've got a softer surface, the contact time is longer, so the maximum force will be less. Same will apply if you are looking at the contact time between you dropping a ball and one being like a hard ball, like a golf ball, or a soft ball, like a squash ball that would squash. One's going to have a longer contact time with the squash ball, and therefore although the change in momentum is the same, the force time graph is going to have that different shape.